In this slide, we're looking at Lenz's law. This is from figure 21.15 from your book. Lenz's law tells us the direction of these induced currents, or it's telling us how nature is responding to some change in flux in a coil or in a closed loop. So when we look at this case on the left, you have a permanent bar magnet with the north pole facing down, and as this magnet is moving downwards towards that loop of wire, you can see that the magnetic field in the downward direction is going to be increasing. Now, nature does not want the magnetic flux to change. It wants to maintain a flux. So as it sees a magnetic field pointing downward, getting stronger, it wants to induce a current in this loop, which will create a counterbalancing field in the upwards direction. And you can see by using the right-hand rule, by putting your thumb in the direction of the current and looking at the curl of your fingers, that a counterclockwise current in that loop will produce a B field in the upwards direction. So this B field in the upwards direction is the loop's response to an increasing B field in the downward direction from that dropping bar magnet. In the next case, we're still dropping the magnet downwards, but we have the south pole downwards and the north pole upwards. So you have a positive B field or an upwards B field getting stronger as the magnet approaches. And so in this case, nature wants to create a B field in the downwards direction. And the way it does that is by inducing a clockwise current in that loop of wire. Again, using the right-hand rule, you'll see that'll create a corresponding downwards B field to counteract the increasing B field in the upwards direction. So in every case, when you look at what nature's doing with Lenz's law, just remember it's trying to keep the flux the same. If you're increasing a magnetic field somewhere, it's going to try and create a B field to balance that out. It's going to try and create some negative B field in that area. The other two cases are similar to those. Here we have the magnet moving away with the north pole down. So there's a B field in the downwards direction that's getting weaker. And nature says, well, I don't want the flux to change. I want that B field in the downwards direction to stay the same. So it induces a clockwise current here in order to generate a B field downwards, trying to maintain that flux for as long as it can. It's going to lose because there's going to be resistance in the wire and there's going to be losses there, but as long as it can, according to Lenz's law, a current's going to be induced to try and maintain the flux. And the final case, we've just flipped that magnet one last time. It's so you would have had a B field upwards. The magnet's moving away, so that upwards field is decreasing. So the current is induced to try and help that upwards B field stay the same, and you get this counterclockwise current in that case. Now, if you take this case that we've talked about before, where you have a U-shaped piece of wire and a bar across it, a conducting bar, and you move that bar to the right. Now here, you'll see we're moving the bar to the right, and the B field is downwards. So there's a flux in this area. Nature wants to keep that flux the same. So as this bar moves to the right, we can induce a current, according to Lenz's law, in that loop of wire, which as the area is increasing, really it's going to say, well, if the area increases, I can decrease that B field. If I get a counterclockwise current in that loop, it will create a B field coming out of the page, out of this display at us. And so by reducing the B field into the board, it's going to try and maintain that flux. And so we see this happening here in the right part of this diagram. As this bar moves to the right, according to Lenz's law, we generate a counterclockwise current trying to maintain that flux. But if you look at what happens, remember that if we have a current in this bar flowing upwards with a B field downwards into the board, we can use the right-hand rule to find that there's going to be a force that opposes that motion outwards. And we should expect that anyway, because as we're moving this bar in there, we're inducing a current, we're producing some potential in a wire. We know that nature's not going to just give us that for free. It's going to oppose that effect. It's going to oppose us trying to generate this current, trying to produce this potential, and we're going to feel this resistive force. So if you have a generator and it's generating power by rotating a shaft in a turbine, for instance, to rotate a coil of wire in a magnetic field, you know that you're going to have to do work to keep that shaft rotating, to keep that coil of wire rotating in that field. You know, you don't just get power for nothing. And this demonstrates that effect for the simple slide wire rod.